It's very bitter.
Like, you don't know what you're doing.
Okay. So we're going to keep going with hypothesis testing steps. So at first it's going to be some writing, and then we'll put an example on top of it. And what we did last time was we talked about assumptions. We talked about this marker is dead. No kidding around. I was so concerned about my sugar, I forgot a marker. But this one should right. There we go. So assumptions. So we said the DV is scale. And then we said random selection, but you can't really do that. So maybe random assignment, if you can. And then, what was the last one? Normal. And we hope we have at least 30 people if it's not normal. It says in step 1 you're supposed to identify the population and the comparison distribution, but I find it much easier to just kind of smush to step 2. So, start at sort of 1.5. We're going to identify who's in the study. So what I always do is you put the sample first. So we're going to list whoever the sample is on the left side, for reasons I'll get to in a minute. And then we're going to list who's the population we're comparing to. So we've got some sort of sample and some sort of population. So Pro is looking to see if our GRE scores are at least average. We have our sample of students that have applied for our master's program versus the general student population. We're going to do we're going to add a null and a research. Oops. Spelling out the window this week. So I'd have my sample here, Hop. And that would be filled in with whatever they were. So don't write sample and population. Fill it in based on the question that you're being asked. And so the one we've done already is a non-directional test, or it's not equal and it is equal. That's kind of all we've talked about. We're going to talk about 2 other ones today. But the null is the one that's equal, so this is the no differences. So nothing happened between the 2, or our GRE scores are the same as everybody else's. For that example, or they're not equal. Sort of a yes. So no, nothing happened. Yes, something happens. And I'll expand upon those in a little bit. But the second step, after I identify my assumption, is to just tell you who's in the study, so who's the study about, and what we would expect to happen. So this is where we generate the hypothesis. And you don't have to write big, long, huge formal sentences. You can write it just like this. So step 3 is to determine the characteristics of the comparison distribution. That's a lot of words. What does that mean? The comparison distribution is what type of test we're doing. So the only thing we've talked about is a z-test. So the only distribution that you know so far is a z distribution. So we're doing z. The next test we'll do t. So we're going to write down all the symbols or numbers that we have. And this is where the layout thing is. So I have my sample here on the left. So I'm going to write all my sample statistics on this side. Which is basically anything in your normal alphabet. So I got my sample mean and my number of participants. And my population on this side, I like flowcharts. I don't know if you guys can tell. Population's on this side, so I'm going to write my population mean. And I usually get sigma. Sometimes they'll give me standard error, but not normally. I see they're nice and lined up. So my mean, but in here feeds into calculating standard error. So I've got n next to my standard deviation because that's going to help me calculate my standard error. So steps 2 and 4 go together, and then 3 and 5. So 3 is setting us up for a calculation. 2 is setting us up for what's our cutoff score. So that's step 4. Step 4 here is what's my critical value, is sometimes what it's called, or cutoff score. Have I talked about this being a race? I know we talked about Rock'em Sock'em Robots. I don't know if I did the race example yet. You'll get tired of it. So today it'll be exciting. Next week I'll be like, okay, I'm over this. Right. So what happens is we've got this distribution. So here's Z. We've been working with Z here. Normal, standard normal distribution. And we've been talking about percentiles and how far away from 0 are they, the Z scores, and then what percent is that. So that's all been leading up to like basically now. So a cutoff score or a critical value is anything beyond that point. So we're talking about in the tails, we would reject the null. We would say that the null is very unlikely. So remember the whole thing with hypothesis testing is that we're trying to get rid of this null hypothesis so our research is the last one standing. And so we have to say that this is very unlikely, which means the probability P% is very small. Yeah.
Is that why, like, in a histogram, outliers are such a problem because they prevent you from rejecting your null hypothesis?
Kind of. They're a bigger problem because they move the mean and they cause a lot of error.
Yeah.
Which then leads to failing to reject.
Okay, makes sense.
Because we're doing this, we're basing this on the standard distribution, so it doesn't have
that's true.
outliers.
But it's gonna.
But our sample outliers would cause
yeah.
problems. Yeah.
So when you would go to do a Z-score, it's going to be off because of the outliers, how they contribute to the
Right, mostly because of the error.
standard error.
So standard errors can be higher than normal. Alright, so sometimes it's also called the critical region, and that's just the area where we're going to reject. So the cutoff score is the actual like line in the sand. Critical region is just the space that we reject. They're all different names for the same idea. So I like to think about this as a race with my Scooby-Doo van, because that's the best I can do for drawing. And what we're trying to do is we start at the start line here, which is always a 0. Okay, 0 is the most common score. It's the peak of the distribution. It's the most likely score, because that means that nothing happened. Because we assume that the null is probably true. But if we start to race our little car, we're going to go both directions right now. We have to figure out where the race ends. So here's our little finish line. It's the best checkered flag I got. Okay. So what we're doing in step 4 is our critical region is figuring out where the finish line is in Z-score terms. So we have to, how much out here do we want to reject? So this goes back to the idea of type 1 error. So I know that's been a while. So type 1 error is the likelihood of rejecting the null when I shouldn't. Remember, first mistake, worst mistake, saying something happened that didn't. So how much out here am I willing to say is a good, acceptable mistake area in a sense? And we traditionally use, you see this a lot as p less than 0.05, p less than 0.01.
Yes.
That's where that number comes from. It is not actual p. So do I have that on the slide? Yes. Okay. So usually we're going to use 5% or 1%. You'll see people write it as p less than 0.05 in a journal. I would prefer you think of this as p critical, or even if you want to think of it as alpha. Because that's what we are. We're setting type 1 error rate. So we're setting how many times do we want to be wrong in a sense. So we reject the null when we shouldn't. Because I don't want you to confuse that with actual p. Okay? So there's my finish line, but my car might keep rolling and I actually might make it out here. So we have an actual percentile of where we ended up, but then we also have our cutoff score of what's good enough. Does that make sense to people? Okay, so P less than 0.05 is alpha. Actual percentile rank is P found. Sometimes people call it. Hey.
So how is this, like, how is P critical or alpha, how is it related to P value?
It is a way to basically, this example of finish lines, it's a way to say that if your car stops for the finish line, you don't reject.
Okay.
If your car passes the finish line, you do reject. So it is very like black and white. Here we reject, here we don't reject.
Okay.
Actual P is just the actual probability for that study.
Okay.
So sometimes it's right over here, sometimes it's okay, so alpha is just the type 1 error rating. So we're going to set this line in the sand thing. We're going to have to also talk about, are we doing tails yet? Oh, no, not yet. I'll come back to it. So, can we figure out what those critical scores would be, given that we're doing this particular thing at the moment? So let me draw 2 of these a little smaller so everyone. So we did equal to and not equal to. So we're assuming it might be lower, it might be higher, don't know. Okay, so if I say it's equal or not equal, I haven't picked a side. So I've got to do lower and higher. So this would be where our GRE scores are lower than normal. This is where they'd be higher than normal. What we're going to do is take 5% and split it up. So we want 2.5% out here in the tails. So since I'm not picking a side, I have to split them up. Or if we're going to do 1%, it's going to be 0.5% in each tail. So there is something nice about these. You can use p-norm, especially on test day if you forget what they are, but they don't change. The next test they change, which is lame. So let's go to Studio. Make this a little bigger. There we go. Alright, so I got p-norm. Oh, here, let me type it in a script so you can see it all the time. There we go. And we said we wanted 2.5%. Oh, no, it's not p-norm. I lied to you. It's q-norm, right? Guys, didn't even notice. That was not on purpose. It's q-norm. P-norm is when you have a z-score and you want to go to probability. At the moment, we have a probability and we want to go to z. So it's q. So q-norm, we put in our probability, which has to be in decimals. So I'm going to do 0.25 for this first one. Okay. And our lower tail, if we want this one, would be true, right? So we want 2.5% and lower. Okay. And it's going to give us negative 1.96. Less than 0.05, this is negative 1.96. Now, this is symmetric, so what's the upper one? 1.96. So this is why z is lovely. But, if you aren't sure, right, now we would just do lower tail is false, and it's going to give us the positive end.
Question, but what's the keyboard shortcut to select one line in R? Is there not, or is there like a way to do that with? Oh, you just click this. Sorry.
No, I just shift down. That's all I do.
Oh, okay.
To highlight the whole line.
Okay, cool. I was just wondering because it's.
No, I don't know. That might be a thing. Okay, so Q norm. Let's try 0.0. 1%, so it's 0.5, 20 is 0.005. Okay, so lower until it's true. It's negative 2.58. Some books say 2.57, but I round up. So that would be the z-score I would need to reach to reject the null. So this is the value of z for your sample that you have to get to say the null is false, therefore the research is supported. So there's a lot of like side maneuvering, right? So we're going to convert from p-values to z, because we're going to get z here in a second. And then if it crosses this z-score, then we say the null's not true, therefore the research is maybe true. Okay, so it's supported. Back to this. All right. So step 4, like I said, goes with 2. So it has to match here. So from 2 to 4, you have to make a match. And that's what that table is about. We're going to go look at that in a second. Step 5 is where I'm going to calculate the actual score. So 4 is our critical score. What do we got to get to reject the null? So you can think about this at the end of the semester when you calculate what score do I got to make on the final exam to make an A. Same idea. 5 is what we actually get. So that goes with step 3, because I'm just going to fill in a formula. We can call it Z actual, Z found. Right. This is Z critical. Right. So we calculate our actual Z. So steps 2 and 4 are about what do we expect to have happen in our experiment. Here are the rules that we're setting up. 3 and 5 is like what actually happened. I don't know why they're in the order they are, but I'm matching the book. A lot of books use this type of procedure. And then what we're going to do for the rest of the semester is take this 6-step thing and change it based on the type of test we're doing. So I'm trying to give you like an overlay of like, here's a way to interpret all these different types of tests. 6 is where I make a decision. Is my Z found in the critical region? So here in the middle, anything close to 0, we basically made a range around 0 that we decided is not good enough. We would fail to reject the null. Anything out here past our cutoff score, or our finish line, bless you, we would reject the null. So I can't just say, is this score greater, is 5 greater than 4, because sometimes we're talking about negatives. So you got to think about it, is it more extreme? Because in theory, a -2 is less than a -1.96, so think about it as more extreme, further out. So here in the middle, you don't reject. Past your cutoff scores, you do reject. Now, at first, this is a little difficult because it's just a lot of new things at once. But once you get the hang of it, people can churn through this. But I really want you at the end to get what does that mean. So if I do I have a slide for this? Yes. We'll come back to that slide in a second. So if I reject the null here at step 6, what am I saying? I've rejected the null. People go, and? What's happening is I'm saying the null is probably not true. So the research is supported, which means there is a difference between scores. So the whole point of this procedure is to get back to, did my study come out the way I think it did? So there is a difference, or if I fail to reject, I didn't find anything. And we don't ever say there is no difference between means. We just sort of say we didn't find anything in this experiment. Because we're scientists, we don't like to admit defeat. Right? So, well, this study didn't show anything. It might be true, it might not be true. So I think that's the general gist of science. Don't admit what you don't know. Okay. All right. So a quick note on that point. This is all about statistical significance. That means the p-value is small. So the likelihood of the null being true is very tiny. Okay. That does not mean that necessarily it's practically useful. So I might reject the null, but it not really be that important. And the next chapter covers how to make that judgment. So we're going to work through rejecting the null or not rejecting the null. So are we supporting our hypothesis or not? But then how much should I care about you rejecting the null? I had like a beautiful moment last semester, where a student sent me a link to an article where they were talking about religious kids are less likely to be empathetic or something catchy in the headline. And she was like, they have 400 people in this study and their like values for effect size, which is the thing we're going to get to, are like really tiny. Why is this printed? Why? And I was like, oh, I've done right in the world. And because even though it was statistically significant, the difference between groups was so small that it was like, really? This is just a catchy headline right now. So I want you also to be able to judge like how practically important it is. So statistical significance and practical importance are different things. So let's do an example. And let's talk about one-tailed and two-tailed tests. So I think the easiest thing to look at for this section is that table that's on Blackboard. This one. So I've actually got 3 different options that you can pick from here. Now, that does not change step 3. 1, 2, 3. But it does change steps 4 and 6. We haven't gotten to the very last column. That's the next chapter. So don't worry about the last column yet. So what is all this about? Well, what we're going to do is a z-test. So z-test is when you have the population mean and the standard deviation. So we have all the numbers from the population. On the next test we'll do when we don't have those numbers, what happens. And then HO and H1, just pretend you don't see HO and H1. That should say Nolan research. And then now one-tailed versus two-tailed tests. So what we did a minute ago was we said that the null was that the sample was not equal to, wrong thing, equal to the population. And the research is that the sample's not equal. So I didn't pick a side. This is called a two-tailed test, or non-directional, because you didn't pick a direction. So when I create, come on marker, stay with me for another couple minutes. My cutoff scores, I do it with 2 different tails, so I have to split it in half. And so we listed them for p less than 0.05. It was both plus n minus 1.96, so there's 2 of them, because there's 2 tails, because I didn't pick a side. Okay. P less than 0.01, we said it was plus minus 2.56. Okay. Oh, no, 8, sorry. I got excited. There's a lot of 6s. So that was the example we did. So I have to have 2 of them because it's a two-tailed test. So there are 2 cutoff scores. The other option that you can do is a directional test. So let me do worse, less than test. I used to call it worse, but that didn't always work out well for people. So we're going to go with the less than test. So the research hypothesis would be that the sample scores are less than the population scores, for whatever that means. So it might mean that the scores are going down, but down might be good. So if you think there's an example about ER emergency times, you want those scores to go down. That should get to you faster. So this isn't really the scores are getting worse, it's just that they're less than the population, for whatever reason. So we've got to have this equals here, but this combination is incorrect. People do this all the time. This is what the most common thing people miss on this set. So what happens if you're predicting less, but then the scores are actually way up here, or higher? So basically we have to say we want only less, and anything greater than or equal to is part of the null. So the null always has to have some form of equals, but it does have to be the opposite of the research. So we've got greater than or equal to, and then less than. Let's get both gators. So we're only going to use one tail, so this is a one-tailed test, or a directional test, because we did pick a direction. Spelling challenged. There we go. So the technical definition of the null is that it's the opposite of the research. So I have to include this greater than, and this is this is what people miss. It's basically everything less than or greater than or equal to. So this is don't reject. This is reject. We can do the same thing on the other side. So higher than. So the sample is less than or equal to the population would be the null. And the research would be that the sample is greater than the population. We would never have equals in the research. So make sure you always stick it in the null. This is still one-tailed because I picked the side, and it's still directional. I'm writing all the names up here because they switch back and forth which one they use in the book. And then we're just going up here. Oop, no, not yes, reject. Come on, marker, hold on. All right. And then this is just that written out. So basically what I drew before. So if the scores are going up, the null is equal to, or less than. So you can write it like this. You don't have to use the fancy symbols in the thing. Scores going down, we've got all of them included, so they are opposites of each other. And then this is the one we started with. So a non-directional or two-tailed test. I predict changes, but no direction.
How does this work with like a Likert scale, or like reverse, like the reverse coding? Is that where you would change if you're doing
reverse coding? You always reverse code it to create the mean first,
okay.
And then you're still predicting based on the interpretation of like the total score.
So like, and you determine it based on your variable, right? So your testing variable.
Like which one of these?
Yeah, like which one you use, yeah. Depending on the,
Yeah, you will determine the hypothesis you pick here based on what you would expect to have happen.
Yeah. So like if you want time, like let's say I want them to be faster at something, would I pick a less than, right?
Right, because you expect the scores to be smaller.
But if I wanted frequency of an occurrence, like strokes in certain amounts of like patients in a sample, I would look at higher than because I want to see like.
Well, I hope strokes you'd want to go down.
Well, yes, but like I mean, like assuming like let's say my research hypothesis is like strokes are more likely in this population.
Then it would be higher.
Yeah,
because you said more likely.
Yeah. It's just sometimes they're backwards and that's confusing.
Right, time is the worst. Because if that one you want, usually if they say faster, you think faster is better, so it should go up, but really faster is a smaller score. So think about which score you want to be smaller and larger to make that decision. Yes, yeah, golf would be a good example for a less than test. Okay, hold that thought. Let's do now the cutoff scores for less than and higher than, which, you know, they're on that table. But if you have a moment and you can't remember, so it's Q norm, and we can use 5%, because we've got 5% all over here, so it's all of our eggs in one basket. So I got 0.05. And we'll do lower tail is true. So it's negative 1.64. So that makes this one positive 1.64. If you take my word for it, that's symmetric. It's not both at once, though. It's only one, because it's a one-tailed test. Then if I do the same thing, but this time for 0.01, it's 2.32 or 2.33. Those don't change. So while you might have to use P norm and Q norm for a specific question, because it'll ask you about percentiles, but for hypothesis testing, these are the 6. And in reality, it's only 4. It's just you have to remember the less than test is negative, greater than test is positive. Which is why, oh, I didn't include them. Lame. I used to have them on the table, but that depends on which p-value you pick. Right? So you could add them to your table if you wanted. But I tried to make it clear. Greater here has to be positive here. Less has to be negative here. Different has to be 2 of them here. Okay, let's try one. And then that'll give us all of Friday to do some examples and take the quiz. Because I know with this, more examples are better, I promise. So, food labeling. I find this topic really interesting, just because I find it interesting. Because the labels for organic and natural and stuff don't actually mean anything. Right, so I guess this is my interest in language overall, but it's become a real big issue because America has such a big obesity problem. And so some interesting research that shows that they put the calories on the menu. Sometimes it helps and sometimes it hurts. So sometimes it helps because people go, oh my God, the Big Mac has how many calories? But sometimes people see it as a better bang for their buck. So they're more economic with it. This was a Freakonomics episode, but I was like, oh, that's so interesting. So people actually eat more calories because they're getting more calories for their dollar, which is like backwards for what they want, right? So they have 25 participants, so there's N. And we're estimating how many calories are in an organic meal, and they guessed. Most people are going to underestimate. The real meal, so the population mean 650 with standard deviation of 250. So they're guessing significantly something different. So if you look at this hypothesis, it doesn't pick a side. Right? We see, given the mean, that it's less. But be sure you're looking at what do they say they want. So this one doesn't pick a side, so it's non-directional. Do I have them written out? No. Okay, I just have the example. So let's try it. So our first step is our assumptions. So is the DV scale? The dependent variables, I'm guessing calories. Right? So what does the mean? I could guess 0. Can't really guess negative. I think lettuce actually has a negative caloric intake because it takes more energy to chew than calories it gives you. But generally, there is a true 0 where there are no calories. Right? So I would say yes, it's a ratio scale. You don't have to write me a saga on those sorts of answers. So second one, can we randomly select? I don't even know who the population is. People? What? Participants. So no, probably not. Can I randomly assign? No, because there's only one group. So for Z testing, you can't really randomly assign people because you don't have groups to randomly assign to. You have a group. So careful interpretation. Correct? So we don't really meet that assumption. But this one's really hard to meet anyway. What's the last one? Normal. I don't know if this is normal. probably not. Right? It's probably negatively skewed, right? Meaning there are lots of high scores and not so many low scores. Or it might be positive skewed. I don't know. So the real question is, do we have enough participants to assume it's normal? So the question for normal is like, n is 25, so we're close. Right? Remember the magic number is 30. So I'm not sure if it's normal. I got 25 people, so I'm kind of close. So that would be the first step. So you can do kind of like, yes, we meet it, no, maybe if we did it this way, we can meet this, that sort of thing. Because usually in these kind of questions don't have quite enough information. So step 2. So we got our null and our research. Who's our sample? These 25 participants. People who guess. Oh, no. It's the people who estimate. But why are we estimating? So this organic guessing. So we've given them a meal that's got the label organic on it. That's the thing that they're manipulating. So it's our group of people who guessed about this organic thing. Versus the real meal. Oop, the real meal. Make up words here. So they're guessing based on the fact that it's got this organic label, but how much is it for reals? Okay. So the number of calories we would guess based on it being organic versus the real thing. Now one thing I saw a student do that I think is pretty good, I was just trying to help her figure it out. She often labeled the DV out here. And so the DV is the actual calories that they guessed. And that just sometimes will help make sure you don't have your DV and your IV mixed up. So these people are guessing based on this organic label. This is the real meal, but the DV, the actual mean, is about the number of calories. You could also label it here next to scale. You don't have to do that. That might just help you make sure that you don't have this be the DV. All right, we picked a non-directional test, so I'm going to do equal to, not equal to. And on Friday, we'll do examples of the other two. That automatically makes step 4, what does it say? So it's 0.05, right? Yeah. Plus m minus 1.96. So because I picked step 2, that automatically makes step 4, or 1.96, because the example asks for p less than 0.05. So that's how 2 and 4 go together. Once you pick 2, 4 is decided. You just have to remember what the cutoff scores are. Now 3 here, our sample mean is 525. Our sample is 25 people. The real meal score, and here too, like once you start labeling these, you might realize like, oh, I've got this wrong. 650 calories. Standard deviation is 250. So that makes standard error 250 divided by the square root of 25, which I think is 50. You guys have seen my terrible math skills. Yeah, so that's 250 divided by 5. Yeah, okay. Math still works today. Now the reason that I have them written like this is because for step 5 over here, that's the order you subtract. So I do mean minus mu, so they're in this same order. 525 minus 650 divided by 50. 2 point something. 2.5. So the reason I tell you to write it like this will especially help once we get to later tests that have more information you have to write down, is that this is the order you're subtracting. You do this one minus this one divided by standard error. So there's a small method to the madness here. Would we reject? Okay, we got negative 2.5. So this is us out here. It's our little group of people guessing calories. So would I reject? No. 2.5 more extreme. Yeah, 50-50 chance. Yes. So we would reject no. But kind of actually, what does that mean? So that answers this question, is there a significant difference? Yes. I've rejected the null, but there's no difference. So it supports the research hypothesis that there is a difference. But that's like super scientific boring terms. What does that mean? Well, what that implies is that they're guessing the lower score. So they're significantly different, and their scores are much lower. Okay, so you can't, in a two-tailed test, once you're done, you can say, yes, it's lower. Because it is. It is significantly lower than expected. But all this stuff on the board would be an answer to one of these types of questions. So this is going to be like basically the essay for this exam. And we'll work some more examples on Friday so you get some more practice with it.
Quick question.
Yes.
The negative 2.5, what, like, symbolically, how would you represent that, and what is that called? 'Cause, like, it's
That
a
is
z-score.
Z. So Z is the number of standard deviations away from the mean. So they are 2.5 standard deviations lower than the population, expected population mean.
And so this is the z-score of your sample. Then.
Yes,
Not
compared
as
to
an
the
individual.
population.
It's because we use standard error, not standard
Right,
deviation.
because this is a group of people. I've got 25.
Okay, that makes sense. Okay, great. I just, for my notes, wanted to have it.
Oh, you're fine.